Meme review. Okay, cool. So hi guys, thank you for coming to my talk, and thank you to USACS for letting me present. Today we'll be talking about fast inverse square root. Really, the origins about this function goes back in 1998, and we'll learn more about the function today and the algorithm behind it. My name is Aline. I like algorithms and stuff, and that's about it. That's all for intro. So any of you guys, I'm assuming most of you here have taken 111 or 112. Does this piece of code make any sense to you? This is one line, assume I is an integer, or actually no, I is a float, that's also a float value.
It's trivial.
Of course, it is trivial, yeah.
It looks like maybe a memory address or some sort of like, I don't remember.
Okay, it's not a memory address.
Top part that I didn't pay attention to.
It's really not a memory address. This is actually, this is a hexadecimal value. It also has a decimal value, yeah.
Is this magic?
Yes. So this value right here, 0x5f37590f, is a magic number. A magic number is a number that does cool stuff, and people really don't know why it does cool stuff. And we're here, at least I'm here, to try to explain why this does what it does. Okay. So motivation here, in 1998, Quake 3 is coming out. It's a game by id Software. And id Software is on the rise. They're making Doom, they're making Quake. And this is the third edition of Quake. And the thing is, when you're playing 3D games, one thing that's really important is normalizing vectors. And in order to normalize a vector, you need to take the inverse square root, which is simply 1 over square root of x, where x is some integer, some float, something. You have to calculate that. And you'd say, okay, this seems pretty trivial. I can just compute the square root, and 1 over that square root is my answer. But the problem is, in 1998, that wasn't fast. We did not have graphics cards back then, and this computation was expensive. But what they did was this instead. Yeah, before we go into that, this is what they tried to compute. These are x, y, and z. Again, we're dealing in 3D graphics. So you have to compute that, and you have every single second you have to compute millions of those. And you have to do those computations fast because you want to have nice lighting and nice shading effects. So how do you do that? Well, this is the code they come up with. And just to give you a brief overview, x2 and y, those are two numbers. What we have to do is compute 1 over square root of x, and then this line right here and that comment is the exact code in the game. They're like, well, what's happening here? So we'll go through this entire code and try to understand what's happening here and why it's such a beautiful piece of art, in my opinion anyway. Any questions before we go on? Cool. So the first thing we're going to try to answer is what this line of code is doing, the last line before the return statement, which is y is equal to y into 3 halves of minus x2. x2 here is x, but halved. That's all it is. And then y and y are again something that we've computed, and we'll see what that is. Okay. So the first thing we're going to discuss, what that line of code is doing one iteration of the Newton-Raphson method. And I'll explain what it does right now. I guess I'll just use this board here. I'll keep that there. Okay. So again, we have to compute 1 over square root of x. So what the first step they thought was, I want to guess an answer. I don't know what the answer is, but let's try guessing. If I can come up with a good guess, I can use this method to somehow refine that guess. And then let's see what happens. So let's assume that I know that this is equal to some constant y. I am guessing that this is equal to some constant y. I don't know what y is, but let's say I've guessed. I've made a good guess that y is equal to 1 over square root of x. Yeah?
How do you know you've made a good guess if you never find out what y is?
We'll get into that later. Okay? That's towards the end, which is why I want to do this first. Okay? Let's say we've made a good guess, and we know that y is. Obviously, there's some error in that guess. If we switch around the terms a bit, we can say 1 over x is equal to y squared, and then I can say, the error in my guess is equal to 1 over y squared minus x. Any questions about this? I've assumed that 1 over root of x is equal to y. Yeah?
You need an absolute value there.
Yeah, I don't for now. Okay? Any questions? I've guessed y, and that's my error statement. That's the difference between my actual answer and what I've guessed. So what Newton-Raphson states is, let's say I have a graph here. I have a function. It goes like this. Okay? This is my f of x. It's a random function. Again, ignore this for now. Let's say that this is my root here, right here. This is what I want. This is my root. This is where my equation is 0. If you think about it, this is also where my error would be 0, and I want to minimize my error. Okay? I guess that, say, a point x1 is my root. I've guessed that. Now Newton states that, draw a tangent line from here and drop it onto the x-axis. Go here. This is x2. Okay? It states that x2 is a better guess than x1. Okay? And then slowly you just take this point here. This is the x2 that corresponds to the line. Draw another tangent line like this. I'm sorry, I guess that isn't a tangent line, but whatever. This is x3. And if you keep doing these many iterations, eventually you'll get to x. Yeah?
So is this a graphical representation of Newton's method, and you keep halving it until you get to the actual thing?
Halving it in what sense?
No, you don't know that you're halving it. You just are supposed to assume that you're getting closer.
Okay.
Okay? I've guessed, my initial guess was x1, that my answer is x1. The root of my equation is x1. Okay? And x is important because that means at that point my error is 0. That means I have an exact guess as to what 1 over square root of x is. Questions about this? And then we just keep iterating through. We guess x2, then we get x3. Okay, and then if we keep doing this, eventually we'll get to x. And that's what we want. Okay? And the thing is, the really nice thing about this is that this converges very quickly. I'm actually going to write what Newton-Raphson's thing is. So it states that x nu, which is my second x, minus f of x over the derivative of f of x. F of x being the function I currently have, f prime of x being the derivative, and x being my original guess. Questions? Does everybody understand why I want to minimize this error here? I want that error to be as close to 0 as possible, because that means I have an exact answer for what 1 over square root of x is. Cool? Okay. So I have x nu, I have x minus f of x over f prime of x, and this is how Newton's method is working. Now instead of f of x, my function is error of y, so we can just compute the derivative. I'm going to skip some computation here, and I'm just going to say error. The derivative here is equal to minus 2 over y cubed. And then if we plug these into that equation, we get a new guess. Actually, I could just move this forward. Yep. So again, new guess here, y minus error of y, error prime of y. And our new guess here is, again, the derivative here is minus 2 over y cubed, and my original function was 1 over y squared minus x. So we have this guess, and then we have the function, then I put values in the function, and then I get this y multiplied in brackets 3 halves subtract half of x into y squared. Again, x is our original number, y is our guess. Questions? Yeah.
Is the Newton method being applied on the actual function whose roots are the inverse square root of x, or on the error function?
On the error function, not the original, not one.
Which you want to make 0. So then, does it converge to 0, or does it converge to?
We're only doing one iteration in our code.
Okay.
We're not doing multiple iterations because the Newton's function converges very quickly. Does that make sense?
Okay.
Okay. Yeah.
For this Newton method, what happens if you have a function with like more than one root?
That's a good question.
Yeah, so then you can do some sort of weird, depending on where you start, there are some like degenerate cases where you oscillate like, back and forth and it can not work. But for square roots, it's fine.
Yeah. The thing is, as a square root, you only plug in a positive value and it only has one root. So for our function, that works. And let's assume that it works.
And if you're close enough to the root, then even if there's multiple roots, it's going to converge to correctly.
Yep. Thanks, Keith. Okay. Any questions about this? The whole idea behind doing this is that we make a good initial guess. And then we just run this one iteration. We can't do more than one because that would involve more computation power. But as we'll see that this thing right here converges super quickly, which is really nice for us. I think I have an Instacalc link here. Okay. So here I want to get what 1 over square root of 2 is. That's what we're trying to compute here. Okay. So initially we just guess it's 1. That's our initial guess. Then we say, okay, I guessed 1 and I want to move forward with that. So then after applying that iteration, we just get this. In our first iteration we get 0.5, which is close but not close enough. And then we guess, after we do another iteration of the method, we get 0.625. Again, close but not close enough. Then we get 0.69, 0.70, 0.707. And then that gets very close. And that's super nice for us. We have a 99.999% accuracy, which is good. We don't need to be 100% accurate, at least not in gaming anyway. Okay, questions? Cool, okay. Okay, so we have this line down. This is most of the algorithmic part of this quote-unquote hack that we're going to talk about today. Let me get rid of this. So the rest is all bit operations. And I'm going to explain what bit operations you need to know, and that's what the talk is actually supposed to be about. So we've established that if we have a guess, and a really good one at that, we can somewhat improve it and we'll be happy. We'll have a nice answer and we can use that to compute whatever we want. We can use that to compute our vector. But the problem is, how do you make a nice guess, right? So this is where they do something super cute. They do this, and then they do this beautiful line of code right here, appropriately commented, obviously. Let me go to present. Okay, so if you've taken 211, I think you've learned about what floating point representation works like. But if you haven't, I can explain it to you. So floats. Okay, I don't need this now. So back in 1998, you had 32-bit integers. They're indexed from 0 to 1. Obviously, 31st being here, and then 30 to 23, and I guess this should probably be shorter. 30 to 23, and then this should be 22 to 0. Mantissa, exponent, sign. Okay. So they have a 32-bit string, and that's how they're using to represent floating point numbers. But really, what does this mean? Okay. So here's what we're going to do. Let's say we have a number x first. I actually want to write this formula down, but I'm not going to explain it before I go further. 1 plus m e minus 127. What?
In your side, it includes a 2 in front of the e.
Oh yeah, sorry, I forgot the 2 here. E minus 127. Yep. Okay. So I'll try to explain how this is going to work. 176 minus 176 0.325. 375, sorry. That would have been a problem. So floats are represented in exponent mantissa form. And really what that means is, let's say I have this number, it's in decimal, base 10, what you're all familiar with. We want to represent this number in a term, in the terms of a computer. We want the computer to understand what this number means with precision. Okay, the way to do that is to represent as a power of 2, take the most significant bit and put it as a 1 and represent the rest as exponents. So the first thing we're going to do is we're going to convert this number to binary. And let's do that first. Actually, let me do it there. I probably need more, but anyway, let's see how that goes. 2 raised to 7, 2 raised to 6, 2 raised to 5, 2 raised to 4, 2 raised to 3, 2 raised to 2. Yeah. Okay. So the first thing we need, let's add a sign bit here as well. Sign. Okay. So the first bit is a sign bit. If it's a negative number, then this value right here, it's added there, is 1. So x is negative, it's a negative number. So we put that as 1. If it was just 176.375, then we put a 0 there. Cool? Okay, so let's get rid of this for now. Now we're left with 176.375. After this, we just find the highest power of 2 that we can subtract from this number such that it remains positive or well, non-negative. And that power is obviously x minus 128, which is equal to, I'll just copy that from there. What is x minus 128? 48.375. Thank you. 48.375. And then 2 raised to 7 is 128. So we put a 1 there. Okay. Then again, we have 48. Of this, we subtract 30 to 16. Thank you. 32. So then we have 16.375. Now 2 raised to 6 is 64. That's not the highest power we can subtract, so we put a 0 there. We have a 32 or 2 raised to 5, we put a 1 there. Questions as to how this is proceeding? Okay, cool. Next, we subtract 16.375. We get 0.375.
You mean you subtract just 16?
What?
Do you mean that you subtract just 16?
Yeah.
Okay.
What?
You wrote minus 16.375.
Oh, oops. Sorry. Thanks. So I subtract 16 and I get 0.375. So we get a 1 there. And then obviously now this is 0.375. So we can't subtract 8 from this, can't subtract 4 from this, can't subtract 2 from this, can't subtract 1 from this. Now these bits right here, they are, a half, a quarter, an eighth, and so on and so forth. And all we need is first we can subtract about 0.25 from this, so 0.250, we left with 0.125. Okay, and that corresponds to 0, 1, 1. And then this is just minus 1.125. Again, this is a pretty easy example, but that's how you'll represent a number. So we have this representation. I'm going to get rid of the sign bit now. This is how you represent just x is equal to 176.375 in binary. Okay? But we have to do something more. This is not in the form we want, and we need to convert it to that form. So let's write this out for a sec. 1 0 1 1 0 0 0 0 0 0 1 1, and then we have a decimal here. Okay. So now this is in base 2. This number can
0, 1, 1.
0 1 1.
Yeah, because you have a 0 in the 2 to negative 1 place.
Move the decimal to the left.
Oh yeah, my bad.
You said an extra one.
It's fixed now, right?
The 2.
What? That's the fix.
You have
Yeah, that's fine.
You have one more 0.
1, 2, 3, 4, 5. 1, 2, 3, 4. Oh, okay. Yeah. -0. There we go. Cool. Now all I have to do, I want to take this decimal place and put it right after this one. This one is the most significant one. That's the one we care about. So let's do that. So we want to put the decimal place here, and we write everything after it. 0, 0, 0, 1, 1 in base 2. But obviously now that we've shifted the decimal, we need to multiply it by something so that we don't lose properties about this. We can't lose this original number. Obviously it still has to mean this. So we can just multiply it by 2 raised to 7. That 7 is the amount we've shifted the decimal place by. Make sense to everyone? So really now this part right here, this is our mantissa. And this is our exponent. So now these 22 to 0, these are the bits that we'll use to represent this part of the equation, and this 7 is what we'll use, what we'll put in here. And the sign is obviously the 0 or 1, since it was initially negative 1, 7, so that sign bit will be a 1. Questions? Cool. I'm going to move forward then. I did it correctly, right? Cool. Okay. Okay. Now we do something else. We do want to write the exponent. It'd be very easy for me to represent 7 in binary. Just go 1, 1, 1, right? And that's how you represent 7 in binary. But if I do that, then I have to assume that I can't represent negative exponents. So in order for them to allow negative exponents, they add something called a bias. In this case, the bias is 127. It's just 2 raised to the 7th power minus 1. That's all they do. So instead of writing 7, now that we have this, to represent in binary, let me get rid of this right here. Okay. Actually, I could just copy it from there, but anyway. Okay. So we have 7 here. What we're going to do is we're going to take 127 plus 7, which is 134, and the bit representation of 134 is what goes in there in order to allow for negative exponents. That's all. If we wanted to do negative 7, then we just go 127 minus 7, 120, and then we'd represent 120 there. If instead of 2 raised to negative 7, we had 2 raised to 7, we had 2 raised to negative 7. You have a question? Okay. Anyways, so we have 134 now, and that's the value that we want to put into our representation. Cool. So overall, after we go through this entire process, we get this huge form. I'm going to explain. Actually, it doesn't make sense for me to write. The first bit right here, that represents the sign. So in this case, the negative sign. If it was a positive number, that bit would be 0. This number is the exponent. That's 134 in this case. Cool. And this part is just the mantissa. That's what we've computed here. Those bits, they go in right here. Obviously, it starts from the most significant, so half, a fourth, an eighth, a 16th goes right to the end. And we stopped at about an eighth, and that's why all the bits afterwards are zeros. Questions? Cool. So we have this formula. In order to, after we've represented our bits like this, in order to get x back, we have to use that formula. So x is equal to -1 raised to the sign 1 plus m 2 raised to e minus 127. Here e is the exponent after the bias which we've added. So initially our e was equal to 7, which after that we added 127, became 134. Now we're just subtracting that 127, get the 7 back, and that's how we can compute. Now let's come back to the original question. We wanted to compute this, right? That's what we want to compute. So we can just put this right here, 1 over square root. I'm going to ignore the sign for now. So I really just want this, 1 plus m 2 raised to e minus 127. For now, I'm just going to call this value right here e minus 127 2 raised to e. Just makes stuff easier for me. Then this just becomes 1 over square root of 1 plus m into 2 raised to e minus e over 2. So that's what we want to compute now instead. Cool? Questions? All right. So let's see what we have to do here. Now that we know how floats are represented, we want to do a bit shift. A bit shift really means, like, let's say I have this number, it's in binary. If I shift the bits right 1, actually I can just show you the code. If I do a right shift by 1, all I'm really doing 110 is moving every single bit to the right once, and this last bit just dies. We kill the last bit. So essentially it's just dividing the number by 2. That's all we're doing. That's all a right shift is. Why is this important? Why do we care about this? The thing is, if you have an exponent in binary and you divide it by 2 just by doing a bit shift, this quantity excluding the negative sign is what you want. That's all you have to do. It's all a bit shift. Not completely, but it does help you. So here's an example. Let's say you have this floating point representation. You shift all the bits to right by 1. So all of this last 0 there, it goes. We don't care about it anymore. But every single bit is just shifted right by 1 place. And your exponent here is divided by 2. Okay? Some edge cases, obviously, this bit, if it's important to us, kind of dies. Every single bit is obviously shifted by 1. But they're not super important because they're after the decimal point. So we don't care about them as much. We're okay with an approximation. Again, we don't have to compute an exact answer here, just something that's very close. The exponent, if it's an odd exponent, so that means this last bit was a 1, it could go into the mantissa and it might screw us sometime. But again, approximation, we don't care. I'm going to hand wave and say it shouldn't matter for the most part. Questions? Cool. I'm going to move forward then. Yeah. So let's come back to what we were talking. We were talking about a magic number, right? Our magic number r is equal to 0 x 5 f 3 7 5 9 d f. That's our magic number. This part in our magic number is the exponent. This part right here is the mantissa. I'm going to make a claim and say that the mantissa doesn't really matter as much. It's a micro optimization at best. It's not what helps us because, let's face it, like, I mean, 2 raised to some e is probably greater than 0.0001. This part is infinitely more important to us than that part, which is why I'm going to say that this part, I don't care. So let's just get rid of all of this and just put zeros there instead for now. We don't care about the exponent. Cool? So the first thing that we do, we had an initial guess y. Okay? But we don't know. So we have x, we want to shift the exponent by, we want to divide the exponent by 2. So what we do is a right shift. So we go I right shift by 1. the right shift divides the exponent by 2, and r, which is our magic number, in this case we're not using what they used, is just this exponent minus this. Cool? Okay. Let's call this exponent, what terminology did I use there? Let's call this ER. Okay? And let's call the exponent in this function E nu. This is equal to the original E divided by 2 minus 127, accounting for bias. Questions about this? Cool. Okay. So then we obviously say our E final will just be ER minus E nu. We want to make sure that this E final is as close to minus, negative E over 2, as closest to that value as we can get, x raised to minus 1 over 2, sorry. Okay? So you go ER minus E nu. ER in this case is just 189. I'm actually going to write this out here. 0, 1, 0, 1, 2, 3, 4, 5. These are all zeros. This part is equal to 189 in decimal. So this is 189, and this E nu we've computed it here, E over 2 minus 127, and then we get 262 minus E over 2. So now this obviously is not equal to minus half. It really depends on what this value of E is. Okay, and here obviously E is biased by a factor of 127. In this case, since we only have positive exponents, we can also say that E is greater than 127. What this does, however, do is give us a very close approximation to minus half, and that's what we want. And the reason why this code is so nice is because it does it without using a single divide operation. Divisions are expensive. We don't want to use divisions. Floating points are even more expensive, and when you combine the two, that means you're using a lot of computation power that you can save, especially back in 1998. So what we're going to do is, rather than use either of those, we're going to come up with something very close, make a very good initial guess, and then just use the Newton-Raphson method, and then we have an approximation, and we're going to use that in our code. Yeah. And then this is what you see. Let's say you have to compute 2 raised to negative 6. You have to compute the inverse square root of 2 raised to negative 6. So you just compute 1 over 2 raised to negative 6 root. So this has to be equal to 2 root cubed. That's what we want, right? So our E biased, that's what that is. This value right here is 2. That's what we have. So it's 121, and then we just go, I guess I could erase this here. E biased is equal to 121. From this we just get rid of 120. Actually we can just use that value there. So compute 62 minus 121 over 2. This would give us that gives us 62. So that's our new exponent. The 2 is our exponent in our function. So we wanted 2 cubed. Instead we just got 2 squared. And that's not, initially it might look bad, but really this is an approximation, and if you do a Newton iteration over it, you get very close to 2 cubed, and that's all you want. So again, here's another example. You have 2 raised to 10. You want to compute the inverse square root, which is 2 raised to negative 5. What you calculate is 2 raised to negative 6 with the same method, and the actual value is 2 raised to negative 5. So you get very close. You make a very good initial guess, and that's what that beautiful code does. Again, this line right here is just converting from float to init, so you can apply a bit shift operation to it, which you do here. Then you subtract it from a magic number that you've computed, which gives you very good initial guesses. Then you retypeset it to a float, and then you do an iteration, a Newton iteration over it, and then you return your answer. And that's all the hack really is. Yeah.
So I in its exponent was already adjusted by the bias, right? So when you right shifted it, shouldn't it be e minus 127 the whole thing divided by 2? Why is it just e divided by 2?
E is just E is the whole.
Exponent, right?
No, E is not the actual exponent. E is the biased exponent.
Okay, it's already biased.
Yeah.
Okay.
Yep. Yep, that's it. Thank you.